Imagine you spend like months engineering this highly complex piece of software. I mean, you are 90% of the way there.
Oh, that is the best feeling.
Right. The core logic is pristine, all your tests are passing, and you just need to make one final, completely trivial addition to export your results.
Let me guess. You pull in a standard library to handle the formatting, hit compile, and...
And suddenly the entire architecture just violently collapses.
Yeah.
It's awful, but it happens all the time.
It really does. And today we are deconstructing a developer's diary that proves why following a computer's automated troubleshooting advice is sometimes the absolute fastest way to destroy your own project.
Yeah, we are looking at a really classic, frankly agonizing trap in software engineering today.
So what's our source for this deep dive?
It's a developer log dated April 23, 2026. It's actually part 117 of this ongoing series called Notes on Haskell Programming.
Written by a developer named Ang.
Right.
Exactly. And this specific log documents this wild descent into a dependency nightmare, and it was all triggered by the really simple desire to just generate an ebook.
Which sounds so easy. But we're going to explore the cascading failures of overriding core system packages. We'll see how a localized fix one that Ang applied weeks prior basically became a ticking time bomb.
A huge time bomb.
So for you listening, this is a deep dive into the mechanics of automated build systems, constraint solvers, and really the broader philosophy of trusting your foundational infrastructure.
It's totally a cautionary tale about the domino effect of troubleshooting, especially in these really highly interdependent ecosystems.
Right. But before everything broke, the context here is super important. Ang was actually operating from a major position of success.
Yeah, they really were. Ang had architected this robust parser that was successfully handling like 90% of their target use cases.
And building a parser isn't exactly a weekend project.
No, not at all. Navigating the edge cases of custom syntax and generating an abstract syntax tree that is notoriously difficult. So Ang had already accomplished the heavy lifting here. The core engine of the project was running beautifully.
Okay, so the natural next phase was to take all that successfully parsed content and just output it as an ebook. And to do that, Ang brings in two really well-known external dependencies.
Right. Pandoc and Pandoc types.
I'm going to frame this for you using a mechanical analogy. Imagine you've spent months machining this beautiful, high-performance car engine.
Okay, the parser.
Exactly, the parser. It's perfectly tuned. Now, you just want to bolt that engine into a highly complex, pre-built chassis and transmission system, which is Pandoc. So you can actually, drive the output into an ebook format.
I like that analogy.
In theory, you just lower the engine into the bay, connect the mounts, and turn the key. Adding a dependency seems like it should be the easy plug-and-play part.
Well, the reality of software integration, especially in a super strict environment like Haskell, is it's never just a simple bolt-on operation.
Not at all.
Because Pandoc isn't just a basic tool. It is essentially the universal translator of document formats. It's massive.
Because adding it isn't just adding one thing.
Right. Adding Pandoc as a project dependency doesn't just add one isolated module. It introduces this sprawling, deeply interconnected web of subdependencies into your project space.
Thousands of new moving parts.
Exactly. Your finely tuned engine suddenly has to interface perfectly with all these new parts, and every single one of them comes with its own rigid set of version constraints.
And as we see in the log, the integration of that complex chassis instantly triggers a catastrophic failure.
Instant.
Ang hits a wall with this very specific error. It's labeled S4804 stack, failed to construct a build plan.
Yeah, Stack is the build tool orchestrating all of this.
And when stack fails to construct a build plan, what does that actually mean under the hood?
It means its internal constraint solver has hit a completely unresolvable contradiction.
Like a math problem with no answer.
Exactly. It's analyzing this multidimensional puzzle of version requirements and determining that a mathematically valid configuration just does not exist.
So what exactly broke in Ang's graph?
Well, the mechanics of the failure are fascinating. Stack operates by building a directed acyclic graph of dependencies. So node A requires node B requires node C, and so on.
But every requirement has boundaries, right?
Right, like demanding a version greater than 3.0 but strictly less than 4.0. In Ang's log, the breakdown happened deep within that graph. Two specific libraries, Cabal Doctus and XML Conduit, were demanding completely different incompatible realities regarding the core Cabal library.
So the graph just couldn't be resolved.
Yep. Stack just threw its hands up.
But wait, modern compilers and build tools are usually super deterministic, right? Like they're very verbose about how to resolve these conflicts.
Usually, yeah.
When a solver fails, it typically spits out a suggested remediation path. It tells you exactly what to do. So my question is, why didn't Ang just follow the compiler's recommended action to clear the error?
Well, that's the thing. Ang's instinct was normally to do exactly that. But the text reveals this critical, really fascinating piece of project history.
Oh, this is the best part.
Yeah, so Ang had actually encountered a localized compilation error back in part 15 of their notes, like weeks before this current crisis.
Weeks ago.
Right. They were trying to install a formatting tool called Formaloo. The compiler hit a snag, threw an error, and explicitly suggested a fix.
And Ang just trusted the machine.
Exactly. They implemented the suggested override to force the installation through. And it worked at the time.
But that automated advice was a trap.
A total trap.
By applying the compiler's localized, kind of short-sighted fix in part 15, Ang inadvertently laid the exact groundwork for the massive recurring build failure we see in part 117.
Right, because compilers and constraint solvers, they operate on local maxima.
Meaning they only look at what's right in front of them.
Exactly. They look at the immediate problem blocking the current execution thread, and they suggest the path of least resistance to clear that specific hurdle. They don't have a holistic vision of your project's future architecture.
So the compiler gave a fix for Formaloo, completely unaware that it was creating a mathematical impossibility for Pandoc, weeks down the line.
Precisely. And to understand why it was mathematically impossible, we really need to examine the nature of that time bomb.
The root cause.
Right. The core of this broken build plan revolves around a concept in the Haskell ecosystem known as a boot package.
Ang explicitly notes how important it is to understand this architecture in the log.
Yeah. So a boot package is a library that is bundled directly with GHC, the core Haskell compiler.
Wait, so these aren't just normal dependencies you download from the internet during the build?
No, not at all. They are pre-compiled foundational libraries. They are assumed to be immutable parts of the compiler's internal reality.
Okay, and Cabal is one of these core boot packages. It's basically the foundational packaging infrastructure for the whole language.
Right.
So going back to my automotive analogy, if the parser is the engine and Pandoc is the chassis, then GHC and its boot packages represent, like, the underlying robotic assembly line.
I love that, yes.
They're the strict factory specifications for every bolt thread. They dictate the immutable laws of physics for the build environment.
And Ang manually altered those laws of physics.
Oh, man.
Yeah. The source code diff shows that Ang placed a hard-coded override for the Cabal syntax library, pinning it to version 3.142.2.0 inside the stack.yaml configuration file.
That sounds a lot like trying to replace the concrete foundation of a house while the walls and roof are already fully built.
That is exactly what it's like. In the factory analogy, they basically told the robotic assembly arm to drop its standard tooling and use this highly specific, non-standard wrench.
And they did that purely because the compiler told them to, back in part 15, to get Formaloo working.
Exactly. The compiler saw a localized issue, realized swapping the wrench would clear the error right then, and suggested the override.
But then we flash forward to part 117.
Right. Ang brings in the massive Pandoc chassis. Stack, acting as the factory floor manager, tries to calculate how to assemble everything. It looks at the dependencies for Cabal Doctist and XML conduit, assuming the standard factory tooling is in place.
But the foundation had been artificially altered.
Yep. Because the foundational reality of the Cabal syntax package had been locked to 3.14.2.0, Stack's constraint solver is completely paralyzed.
It just couldn't resolve the version requirements for the new Pandoc web because the boot package was manipulated into a state that conflicted with the broader ecosystem.
Exactly. The artificial override just shattered the solver's ability to compute a valid build graph.
It's literally a self-inflicted wound disguised as an automated solution.
It really is.
So knowing that the manual override caused this entire mess, how does Ang finally untangle it? How do they get back to generating this ebook?
Well, the fix required stepping back from the localized error and addressing that architectural foundation. Ang resolves this not by writing, more complex constraint overrides, but by deleting the trap entirely.
The cleanup involves two really precise tweaks, right?
Yeah. The first step is structural cleanup. Ang goes directly into the stack.yaml file and completely deletes that extra Cabal syntax 3.14.2.0 dependency.
They just wipe out the artificial instruction that was confusing Stack.
Right, returning the robotic assembly arm to its standard factory default tooling.
Okay, but simply removing the bad instruction leaves a vacuum. The build tool still needs to know what set of global rules to apply to the newly introduced Pandoc dependencies.
Exactly. Which brings us to the second step of Ang's resolution. This happens in the package.yaml file. Ang deliberately bumps the Cabal version from 3.8 up to 3.12.
Okay, wait, let me jump in here. Why specifically bump it to version 3.12? Is that just like a random lucky number they guessed until it finally compiled?
No, not at all. Bumping to 3.12 was a very deliberate move. That specific number is chosen to align the project tightly with the ALT's 24.26 snapshot.
The LTS, long-term support.
Right. The LTS snapshot is really the key to escaping dependency hell here. In these complex, strict environments, an LTS snapshot serves as this pre-computed, heavily verified matrix of compatible library versions.
Basically a giant map.
Exactly, a massive map drawn by ecosystem maintainers. And it mathematically guarantees that if you use this exact set of versions across thousands of libraries, the constraint solver will successfully build the graph.
There will be no contradictions.
None.
So by aligning the project with the LTS 24.26 snapshot via that 3.12 version bump, Ang fundamentally shifted their whole strategy.
They did. They stopped trying to micromanage individual package constraints.
Right. And instead deferred to the pre-verified harmony of the ecosystem.
Yeah.
They basically trusted the LTS map to automatically pull the correct intercompatible versions for Cabal Doctist, XML Conduit, and all of Pandoc's crazy subdependencies.
Yep. And the log distills this journey into a very strict architectural rule. Unless it is absolutely necessary, or you are operating at the compiler development level and know exactly how to manage the fallout, do not override boot packages.
Or any core libraries that come pre-installed with GHC.
Exactly. Overriding a boot package undermines the foundational assumptions of the build tool. It breaks the internal logic that the constraint solver relies upon, and it inevitably leaves your build plan in ruins.
So just to recap the journey for you listening, we went from a really robust 90% functional parser to a total system failure.
And the failure wasn't even caused by a flaw in the parser or a bug in Pandoc?
Right. It was the detonation of a time bomb planted weeks earlier, all because the developer trusted a compiler's localized, short-sighted suggestion to manipulate a foundational boot package.
And the system was repaired only when the developer removed that localized override, stepped back, and realigned the project's configuration with the broader, pre-computed stability of the LTS snapshot.
It's a huge lesson in respecting the structural integrity of your infrastructure, rather than trying to micromanage the core foundation.
Absolutely.
And it leaves you with something pretty wild to think about. I mean, this hyper-advanced compiler, a tool engineered on principles of pure logic, confidently provided the exact advice necessary to sabotage the developer's future architecture.
It was so confidently wrong.
Right. If the machines we rely on to parse absolute logic can be that confidently wrong when constrained by a lack of holistic vision, it makes you wonder, how much of modern problem-solving is actually just learning when to ignore the machine's suggestions and look at the bigger picture?
That is the real challenge of engineering.
It really is. Well, something to chew on next time your compiler gives you a helpful hint. See you on the next deep dive.